In 1916, a dying man in a frozen trench solved an equation that accidentally predicted two objects. We spent the next 109 years confirming one of them and quietly pretending the other does not exist. The same equation that gave us black holes has been quietly insisting on a second object, a region of space-time that nothing can enter and everything must leave. The opposite of a black hole in every direction at once. The math demands it. Reality, as far as we can tell, refuses to build it. But here is the part that keeps the lights on at night for theoretical physicists. When you list the properties of this forbidden object on a piece of paper and compare them to the Big Bang, the lists match. So settle in, friend. Hit subscribe if you are new here, and tonight let us walk slowly through the possibility that the universe you're sitting in began as the very thing it is supposed to forbid. Part 1. The second impossible object. In 1916, a single page of mathematics described two objects at once. One of them, the world eventually accepted. We named it the black hole, we photographed it in 2019, we listened to two of them collide using gravitational wave detectors, and we built entire careers studying it. The other object on that same page, born from the exact same equations. The world has spent more than a century quietly pretending does not exist. It is sitting right there in the math. Almost no popular science channel will talk about it for more than 30 seconds. And the reason for that silence is what this entire video is about. The forbidden object has a name. Physicists call it a white hole. And the simplest way I can describe it to you is this. Take everything you know about a black hole and run it backwards in time, like a film reel reversed in the projector. A black hole is a region of spacetime that nothing can escape. Not even light. Not even information. Not even causality itself once you cross the line. A white hole is the perfect inverse. It is a region of space-time that nothing can enter. Matter, light, and information can only stream outward from it. You cannot push a single photon into a white hole, no matter how hard you try, in the same way that you cannot push a single photon out of a black hole. One swallows, the other vomits. They are the same equation, just pointed in opposite directions on the clock. Now, you might already be thinking, that sounds like science fiction. It really, really does not. White holes are not some clever idea that a novelist invented in the 1970s. They are a direct mathematical consequence of Albert Einstein's field equations of general relativity. The same equations we use to design GPS satellites, to predict the orbits of planets around distant stars, and to interpret every single gravitational wave detection LIGO has ever made. If you believe in black holes, and you should, because we have photographs of them now, then the equations that gave you black holes also gave you white holes for free. They came in the same package. They were never separable. Here is where the emotional contradiction begins. General relativity says they are allowed. The second law of thermodynamics, which is the law that says entropy always increases, that broken eggs do not unbreak themselves, that smoke does not gather back into a candle, says they should be impossible. So you have two of the most successful theories in the history of science staring at each other across a table and disagreeing about whether one specific kind of object can exist. That is the puzzle. That is the forbidden object. And I want you to remember that phrase, the forbidden object, because we're going to come back to it again and again. For most of the 20th century, white holes were treated like an embarrassing cousin at the family reunion. Physicists would acknowledge them in equations, then change the subject. Textbook authors would mention them in a footnote. Graduate students were quietly told not to spend their dissertations on them if they wanted a career. But something changed in the past 15 years, and it changed because black holes themselves stopped behaving the way we expected. Stephen Hawking found a paradox involving information. Quantum gravity researchers found that singularities, those infinite density points at the center of every black hole, probably do not actually exist in nature. And once you remove the singularity, you are left with a question. If a black hole does not end in a point of infinite density, what does happen when you fall in? What is on the other side? Several of the most respected theoretical physicists alive today, including the Italian physicist Carlo Rovelli, have a strange answer to that question. They believe that black holes eventually transition into white holes, not metaphorically, not as a thought experiment, as a literal physical process governed by quantum gravity. We're going to spend a lot of time on Rovelli later, because his work is at the centre of why this conversation has come back from the dead in 2026. But for now, just sit with the implication. Somewhere in the observable universe tonight, while you and I are sitting here, an old black hole billions of years old may already be beginning the transition. The process may already have started, and here is the larger mystery that we have to address head-on, because it is what gives this whole topic its weight. The Big Bang itself, the event that gave birth to everything, every atom in your body, every galaxy in the sky, every photon of starlight you have ever seen, shares a list of properties with white holes that is a little too long to be a coincidence. Outward expansion of spacetime, an inaccessible origin you cannot travel back into, an enormous release of energy, an incredibly low entropy starting condition. If you were handed a list of those 4 properties on a piece of paper with no label at the top and asked what kind of object this describes, a working physicist would probably tell you that is a white hole. So here is how we're going to do this, you and I, over the next several hours of equivalent reading. First, we're going to walk through the equations, slowly and gently, with no math required from your end. Then we're going to walk through the paradox, the place where the equations and reality fight each other. And then finally we're going to walk into the cosmological implications, which are some of the strangest ideas ever proposed by serious scientists. Because the frightening possibility is not that white holes exist somewhere far away in some distant corner of the cosmos. The frightening possibility is that the universe itself may have begun as one. Stay with me. Part 2, A Dying Man in a Trench. To understand how we got here, I need you to picture something with me. It is December of 1915, somewhere on the eastern front of the First World War, in what is now somewhere between Poland and Belarus, there is a German artillery officer crouched in a trench. He is 42 years old. His uniform is damp from the cold and from the rain that froze and then melted again into mud. The candles in the dugout are burning low because they cannot afford to burn many at a time. There is the sound of distant shell fire, the muffled thump of explosions a few kilometers away, the kind of sound that you stop noticing after a while because if you noticed it every time, you would lose your mind. His name is Karl Schwarzschild. By trade, he is one of the most respected astronomers in Germany. He used to direct the Potsdam Astrophysical Observatory. He has published papers on optics, on stellar atmospheres, on the geometry of light. But right now, in this trench, he is doing something else. He's doing calculations on a piece of paper between artillery firing tables, working out problems that have nothing to do with the war and everything to do with a paper that just arrived from Berlin. The paper is from Albert Einstein. Einstein has just published in November of 1915 the final form of his theory of general relativity. The field equations of gravity. The whole thing. And almost nobody in the world has fully understood what he has written down because the math is brutal. It involves what are called tensor equations, 10 of them, all coupled to each other, all describing how mass and energy curve the geometry of spacetime itself. Einstein himself, when he published, did not have an exact solution to his own equations. He had only approximate solutions. He thought it might take years before anyone produced a clean, exact answer. It took Schwarzschild a few weeks, in a trench, with shells falling. He sent his solution back to Einstein in a letter dated December of 1915. Einstein read it and was, by his own admission, astonished. Einstein wrote back with a line that has become one of the most famous compliments in the history of physics. He said, "I had not expected that the exact solution to the problem could be formulated so simply." Coming from Einstein, that is the equivalent of being knighted. He presented Schwarzschild's solution to the Prussian Academy of Sciences in January of 1916 on Schwarzschild's behalf, because Schwarzschild, of course, was still on the Russian front. What Schwarzschild had written down, on those pieces of paper, between calculations about how to aim artillery shells, was an equation that nobody fully understood at the time, including Schwarzschild himself. Embedded in his solution were predictions of objects that would not even be named for another 50 years. Event horizons, singularities, black holes, white holes, the mathematical skeleton of what we now call wormholes. The trench in which he was sitting was, without exaggeration, the birthplace of every black hole image you have ever seen. He never knew what he had done. By the spring of 1916, he had developed an autoimmune skin disease called pemphigus, which in those days, before any kind of effective treatment, was essentially a death sentence. He was sent home from the front, deteriorating quickly. He died on May 11, 1916, at the age of 42, only a few months after solving Einstein's equations. He never heard the phrase black hole. The phrase did not exist yet. It would not be coined until John Wheeler used it, more or less by accident, in a lecture in 1967. Schwarzschild never knew that the Event Horizon Telescope would, in 2019, take a photograph of the supermassive black hole at the centre of the galaxy Messier 87, and that the size of the dark shadow in that image would be calculated using his equation. He never knew that the gravitational waves LIGO detected in 2015, exactly 100 years after his death, came from two black holes whose existence he had unknowingly predicted in a trench. I want you to feel the weight of that for a second, because it really matters for what we are about to discuss. The same equation that predicted real, observable, photographable black holes, the equation that the entire modern field of gravitational wave astronomy traces back to, also predicted white holes. We accepted one half of his discovery. We have spent 109 years quietly avoiding the other half. We took the part that fit our intuitions. We left the part that did not. And the question I want you to keep in your head as we go forward is, what if we do not get to choose? What if the math is a package deal? What if accepting the universe of black holes means we eventually have to accept the universe of white holes too? Because Schwarzschild's equation, the one written by candlelight on the Russian front, has not been falsified. It has never been wrong. And it still has that second object sitting right there in the structure, waiting for us. Part 3. The equation that accidentally opened reality. Let me try to give you an honest sense of what Schwarzschild actually wrote down, without making your eyes glaze over with tensor calculus, because you do not need any of that to understand the strangeness of it. What he produced is now called the Schwarzschild metric. It was the first exact solution to Einstein's field equations. And the simplest way I can put what it describes is this. If you have a non-rotating, electrically neutral spherical mass sitting alone in empty space, the Schwarzschild metric tells you exactly how spacetime is shaped around it. That is the foundational picture that general relativity gives you. Mass and energy do not pull on objects with some mysterious invisible force. They bend the geometry of spacetime itself, and other objects then move along the bent geometry. The Earth is not pulling the Moon. The Earth is creating a kind of dent in the four-dimensional fabric of spacetime, and the Moon is rolling around in that dent. Gravity in this picture is not a force at all. It is geometry. It is the shape of the room you are walking through. You think you are moving in a straight line. The room itself is curved. So what Schwarzschild did was solve, for the first time, the exact shape of that curvature around a single ball of mass, and buried inside his solution was a number, a specific radius, a particular distance from the centre of any given mass at which something extremely strange happens. We now call it the Schwarzschild radius. The formula is r subs equals 2gm divided by c squared, where g is Newton's gravitational constant, m is the mass of the object, and c is the speed of light. You do not need to memorize that. What I want you to get is the scale. For our Sun, which is a perfectly ordinary star with a mass of about 2 × 10 to the 30th kilograms, the Schwarzschild radius is about 3 kilometers. That is roughly the size of a small town. So if you took the entire Sun, all of its mass, and compressed it down into a sphere about 3 kilometers across, it would become a black hole. For the Earth, which is much less massive, the Schwarzschild radius is about 9 millimeters, smaller than a marble. If you crush the entire Earth, all the oceans, all the continents, the molten iron core, every living thing, down to the size of a small marble, the result would be a black hole that would slowly over time eat anything that came too close. Of course, in the real world, the Sun and the Earth are far larger than their Schwarzschild radii, so they are not black holes. But for objects that are sufficiently dense, that have been crushed by their own gravity past their own Schwarzschild radius, something happens at that radius that defies normal intuition. It becomes what we now call an event horizon, a one-way causal boundary in the universe. Once anything crosses inward, it cannot get back out. Not because it is not strong enough, not because it does not push hard enough, because the very direction it would need to travel in order to escape no longer exists in its future. I want to slow down on that last point, because it is the single most important thing to understand about the interior of a black hole, and it is what makes white holes feel inevitable. Inside the event horizon, the Schwarzschild metric does something genuinely bizarre. The roles of space and time effectively swap. Outside the black hole, you can choose to stand still in space, but you cannot stand still in time. Time will keep flowing forward whether you want it to or not. You can move left or right or up or down, but you cannot move backwards in time. Inside the event horizon, the coordinate that used to represent moving inward in space starts behaving like time, which means, once you are inside, moving toward the singularity at the center is no longer a choice. It is no longer a direction you can decline to travel. It becomes as inevitable as moving into tomorrow. The center of the black hole is, for you, the future. You cannot avoid your future. You can only delay how quickly you reach it. Now, here is where it gets really interesting, and here is where the second object enters the story for real. When physicists in the 1950s and 60s, people like Martin Kruskal and George Shikarus, sat down and worked out the full mathematical extension of Schwarzschild's solution, they found something none of them were looking for. The Schwarzschild metric, fully extended, does not just describe a black hole and the universe around it. It describes 4 distinct regions of spacetime, all stitched together by the same geometry. There is our universe outside the black hole. There is the interior of the black hole, the region you fall into and cannot escape from. And then there are 2 more regions that nobody asked for and that the math will not let go of. There is a second universe, disconnected from ours. And there is a region whose interior is the time-reversed mirror of the black hole interior. A region you cannot enter, a region from which you can only emerge. That 4th region is the white hole. It was not added later by speculative physicists with too much imagination. It was not a desperate attempt to make the equations more interesting. It was always there. It is what Kruskal and Shikarus found waiting for them when they finished the homework Schwarzschild had assigned 40 years earlier. The black hole has a future singularity at its center, the place that everything inside is forced to fall toward. The white hole has a past singularity, a singularity in the past from which everything is forced to emerge. If you let that sink in, you start to feel why this is hard to dismiss. The universe of the equations contains both. The universe of our observations seems to contain only one, so either the equations are telling us something is missing from our observations, or the equations are too generous, and reality picks and chooses what it actually instantiates. Most physicists throughout the 20th century made peace with the second option. They said, the equations describe an idealized eternal black hole, a black hole that has always existed and always will exist. Real black holes form from collapsing stars, and that process does not produce the white hole region. The math is too perfect for our messy universe, but that argument has gotten weaker over the past 2 decades. And the reason it has gotten weaker is exactly the reason we are having this conversation. White holes, you have to remember, were never invented. They were discovered accidentally, by people who were just trying to do bookkeeping on Schwarzschild's solution. The forbidden object did not climb out of someone's imagination. It climbed out of a textbook, and the question we still cannot fully answer, more than a century later, is what to do with it. Part 4, the Penrose diagram and the 4th region. In the 1960s, a young British mathematical physicist named Roger Penrose sat down to draw a picture of all of this. Not a graph exactly, not a chart, a picture. Penrose realized that if you wanted to genuinely understand the structure of space-time around a black hole, you needed a way to see it all at once. The whole infinite stretch of past and future, inside and outside, compressed onto a single page. So he invented something called a conformal diagram, which the physics community now usually just calls a Penrose diagram. And these diagrams have, more than any equation ever written, shaped how working physicists actually think about black holes in their heads. Here is the trick of a Penrose diagram. Space-time, in reality, stretches out infinitely in space and infinitely in time. You cannot draw infinity on a finite piece of paper. So Penrose found a way to mathematically squeeze the whole infinite expanse of space-time onto a finite diamond shape, while preserving the one feature that matters most for causality, which is the angle that light rays travel at. In a Penrose diagram, light always moves at exactly 45 degrees. This means that any 2 events you can connect with a 45-degree line, light could travel between them. Any 2 events that would require travelling at a steeper angle than 45 degrees, nothing could ever connect them. Causal structure, the question of what can affect what, becomes a literal visual property of the diagram. You can read it with your eyes. When you draw the full Penrose diagram for the Schwarzschild solution, the eternal black hole geometry, you do not get a single diamond. You get 4 regions stitched together into something that looks a little like a kite or a 4-pointed star. There is region 1 on the right, which is our universe, the asymptotically flat spacetime that we live in. There is region 2 at the top, which is the interior of the black hole, with its future singularity drawn as a jagged line at the upper boundary. There is region 3 on the left, which is a second, completely disconnected universe. And there is region 4 at the bottom, which is the white hole interior, with its past singularity drawn as a jagged line at the lower boundary. I want you to do something with me, just as a thought experiment. Imagine you are standing in the middle of that diagram. Look up. Above you is the black hole. If you walk in the direction of up on the diagram, you will eventually cross into region 2, and once you do, the future singularity at the top of region 2 will become your unavoidable destiny. Now, look down. Below you is the white hole. If you tried to walk down on the diagram, you would find that you cannot. Region 4 is in your past. The white hole did not produce events that you are causing, it produced events that produced you. Anything emerging from region 4 is something you might receive. It is not something you can send. The white hole region is mathematically unavoidable in this geometry. It is not added by hand. It is not a patch. It is what the diagram looks like when you draw the eternal Schwarzschild solution honestly. And that geometry contains another feature, sitting between regions 1 and 3, that I want to mention because it has its own popular reputation. Connecting our universe on the right to the disconnected universe on the left, through the throat of the diagram, is what is called an Einstein-Rosen bridge. Most people know it by its more romantic name, a wormhole. Now, before you get too excited, I have to tell you the bad news. In the classical Schwarzschild solution, the Einstein-Rosen bridge is not traversable. You cannot use it to travel between universes. The throat of the bridge collapses faster than light can cross it. Anyone who tried to walk through would be crushed by the geometry itself before reaching the other side. There are speculative ideas going back to Kip Thorne in the 1980s and continuing into the present about whether you could prop a wormhole open with what is called exotic matter, matter with negative energy density. Those ideas are mathematically consistent but observationally unsupported. What I want you to take away is just this. The full geometry of an eternal Schwarzschild black hole contains a black hole, a white hole, 2 universes, and a wormhole. All of it falling out of one equation written in a trench in 1915. There is a reason Penrose diagrams change how physicists think. Once you have stared at one for long enough, space-time stops feeling like a stage on which events happen and starts feeling like architecture, like a building you could walk through. The black hole and the white hole are not separate buildings, they are different rooms in the same house. Penrose, by the way, won the Nobel Prize in Physics in 2020, partly for his theorems showing that the formation of singularities inside black holes is essentially mandatory under general relativity. He proved mathematically that if a star collapses past a certain point, a singularity must form. Penrose is the reason we take black hole interiors seriously. And the diagrams he gave us are the reason we cannot pretend the white hole region is not sitting right there on the other side. The full geometry of black holes already contains the other side. The forbidden object lives inside the same architecture as the object we accept. They are not strangers, they are reflections, which means, if we want to understand black holes properly, we cannot keep skipping past the half of the diagram that makes us uncomfortable. We have to ask the next question. Why does our universe seem to instantiate one half and not the other? Part 5. Why reality appears to hate white holes. The reason has a name. It is called the second law of thermodynamics, and once we wade into it together, you are going to start seeing why white holes are not just rare, they are not just unobserved. They are, by the most fundamental logic we have, the kind of thing the universe actively resists building. Let us do this slowly, because thermodynamics is one of those subjects that sounds harder than it is, and most explanations make it harder still. Forget the formulas for a second. Just think about your own life. Smoke from a candle disperses into the room. It does not gather itself back into the candle. A glass of milk knocked off a counter shatters on the floor, and you can replay that video as many times as you want, but you will never see the shards reassemble themselves into a glass and leap back up onto the counter. Memories form about events that have already happened, never about events that have not happened yet. You can remember last Tuesday. You cannot remember next Tuesday. Time, in your experience, has a direction. There is a thing that comes before and a thing that comes after, and the universe does not let you mix them up. Why? The most honest answer modern physics has come up with is because of entropy. Entropy is, very loosely, a measure of how many ways the microscopic pieces of a system can be arranged while still looking the same on the outside. A glass on the counter is an extremely specific arrangement of atoms. A pile of broken glass on the floor is an extremely unspecific arrangement. There are vastly more ways for the atoms to be in the broken arrangement than in the intact arrangement. So when something random happens, the system is overwhelmingly likely to end up in the more probable, higher entropy state. Not because the laws of physics push it there, because there are simply more ways to be there. The second law of thermodynamics, in its simplest form, says that the total entropy of an isolated system tends to increase over time. And that statistical fact, weirdly, is what gives time its arrow. The past has lower entropy. The future has higher entropy. We perceive the flow of time because we are watching that gradient unfold around us. Now, here is where black holes come into the picture in a very strange way. In the 1970s, Jacob Bekenstein and Stephen Hawking worked out what the entropy of a black hole actually is. The answer surprised people. The entropy of a black hole is proportional to the surface area of its event horizon. The exact formula, sometimes called the Bekenstein-Hawking entropy, is S equals K times A divided by 4 times the Planck length squared, where A is the area of the horizon and K is Boltzmann's constant. And what that formula tells you, when you actually crunch the numbers, is that black holes contain unbelievable amounts of entropy. A stellar mass black hole, just the kind that forms when a giant star collapses, has more entropy than every star, every planet and every speck of dust in an entire galaxy combined. Black holes are, by an enormous margin, the highest entropy objects the universe has ever managed to produce. Now flip this round. A white hole is the time reverse of a black hole. If a black hole has the highest entropy of any object we know, then a white hole must have the corresponding low entropy starting condition. Which is to say, a white hole would require an arrangement of matter and energy so improbably ordered that the second law of thermodynamics looks at it and sees something close to a violation. White holes do not just have low entropy. They have absurdly, almost incomprehensibly low entropy. This is why physicists routinely describe them as thermodynamically forbidden. But I have to be careful with that word, forbidden, because it is not as absolute as it sounds. The second law of thermodynamics is a statistical law, not a mechanical one. It does not say that low entropy states cannot exist. It says they are extremely unlikely to spontaneously occur. A white hole is not impossible the way a square circle is impossible. It is impossible the way it is impossible for all the air in your living room to spontaneously rush into one corner and leave you suffocating in a vacuum. There is no law that strictly forbids it. There are just so many more ways for the air to be evenly distributed that you can wait the entire age of the universe and never see it happen by chance. So white holes are not strictly forbidden. They are merely statistically unimaginable. And here is where the entire video starts to fold back on itself, because there is exactly one event in the history of the universe that fits the description of statistically unimaginable. Exactly one event with absurdly low entropy that, by every measure we can devise, should not have happened by chance. That event is the Big Bang. The reason the second law works at all in our universe, the reason time has a direction, the reason the past is different from the future, is that the universe began in an unbelievably ordered state, a state so ordered, so finely tuned, that it looks almost exactly like the description of the forbidden object we just spent 100 years pretending could not exist. So what do we do with that? If entropy forbids white holes, then how did the universe itself begin in a state that looks like one? I think you can feel where this is going. Let us keep walking. Part 6. The biggest problem in cosmology is not expansion. When most people think about the great mysteries of cosmology, they think about the expansion of the universe. They think about dark matter, dark energy, the accelerating recession of distant galaxies. These are the topics that get the headlines. But there is a deeper problem, one that the working cosmologists I have read and listened to talk about with a kind of nervous reverence. They call it the past hypothesis, and it is, in my honest opinion, the strangest unsolved problem in physics. Stranger than dark matter, stranger than the cosmological constant, Stranger than any of the fashionable mysteries, the past hypothesis is the assumption you have to make in order for the laws of thermodynamics to work in our universe. It says simply that the universe began in a very low entropy state. We do not know why. We have no derivation of it from deeper principles. We just have to assume it as a starting condition, because if we do not assume it, the second law of thermodynamics does not predict the world we see. The universe behaves as if its initial state was extraordinarily, almost impossibly ordered, and everything since has been a slow downhill slide toward higher entropy. How impossibly ordered! Roger Penrose, the same Penrose we met with the diagrams, has done a calculation of just how special the initial conditions of our universe were. The number he came up with is, I would argue, the most extreme number in all of science. He estimated the probability of our universe's initial state being as low entropy as it was, by random chance, at 1 part in 10 to the 10 to the 123rd power. I know that number does not mean anything to you when I say it out loud. So let me try to give you a feel for it. Take 10, multiply it by itself, you get 100, multiply 10 by itself 123 times, and you get a number called 10 to the 123rd. That is already a number larger than the total number of atoms in the observable universe. And now, take 10 and raise it to that power, to a number larger than the number of atoms in the cosmos. The result is so vast that you could not write it down in normal notation if you covered every square meter of the observable universe in zeros. A normal physicist looks at numbers like 10 to the 80th and feels uncomfortable. Penrose's number for the specialness of the initial state of the universe is more zeros than there are particles in the cosmos. That is what the Big Bang demands, in terms of fine-tuning of its initial entropy. That is the price tag on the universe you're sitting in, and nobody knows how to pay it. Inflation, the well-known theory that the early universe underwent a rapid expansion in its first tiny fraction of a second, helps explain a lot of things. It explains why the universe is so smooth and uniform on large scales. It explains why distant patches of sky have nearly identical temperatures. But, and this is something I think a lot of explanations skip over, inflation does not by itself explain the entropy problem. To start inflation in the first place, you need a low entropy initial condition, and the low entropy of that condition is, in some accountings, even harder to explain than the smoothness inflation was invented to handle. It pushes the question back. It does not solve it. This is why some cosmologists, including Sean Carroll, who has written and lectured extensively about the arrow of time, will quietly tell you that the entropy problem is, in their view, deeper than dark matter, deeper than dark energy, deeper than any of the more famous cosmological mysteries. The reason it does not get the spotlight is that nobody has any idea how to test a solution to it, so it gets relegated to the margins, even though it sits at the centre of why time has a direction at all. Here is the part where everything we have been building starts to click together. White holes also require extremely low entropy initial conditions. That is, in fact, the reason the second law of thermodynamics is supposed to forbid them. But our universe began with an extremely low entropy initial condition, which means, structurally, the Big Bang has the exact property that makes white holes seem impossible. The defining feature of a forbidden object is also the defining feature of the very real, observable beginning of everything we know. You can call that a coincidence. A lot of physicists for a long time did call it that. But coincidences of that magnitude get harder to defend the longer you think about them. The exact thing that makes white holes look impossible is the exact thing the universe itself somehow managed to do at its own beginning. So either the universe did something forbidden, or the rules we use to declare things forbidden were never quite as airtight as we thought, or, and this is the option that has been gaining traction over the past 15 years, the universe did not begin from nothing at all. It began from somewhere, from a structure, from possibly the same kind of object Schwarzschild's equations have been quietly predicting all along. We are not at the answer yet, but the question is becoming impossible to avoid. Part 7. The Big Bang has white hole properties. I want to put this side by side with you, because once you see the parallels laid out, it becomes very difficult to unsee them. Take a white hole, as predicted by the Schwarzschild solution. Now take the Big Bang, as described by modern cosmology. Compare them feature by feature. First, both involve outward expansion of spacetime. A white hole is, by definition, a region from which everything must move outward. Matter, light, and information stream out of it and never return. The Big Bang in modern cosmology is described not as an explosion of stuff into pre-existing empty space, but as an expansion of space-time itself. The fabric of the universe is stretching, and everything embedded in it is being carried apart. Outward expansion, check. Second, both have an inaccessible origin. You cannot enter a white hole. Matter and light are forbidden from going in. Time only flows outward from it. The Big Bang, similarly, is something you cannot travel back into. There is no point in space you can fly your spaceship to where you would arrive at the Big Bang. The Big Bang is in the past everywhere at once. It is not a place. It is a boundary in time you cannot cross. Inaccessible origin. Check. Third, both involve enormous energy release. A white hole would, by its mathematics, eject huge quantities of energy and matter in the process of forming and existing. The Big Bang released the entire energy content of the universe in one event whose details we still do not fully understand. Energy release. Check. Fourth, both require a low entropy starting condition. We just spent a long time on that one. Check. When you list those four properties together with no label at the top, and ask a working physicist to describe the object, they would not say Big Bang. They would say white hole. The Big Bang is structurally indistinguishable from a particular kind of white hole event in the history of space-time, and a number of cosmologists very quietly and very carefully have been pointing this out for decades, only to be told that the resemblance is superficial. I want to address something head-on though, because it is a common confusion. The Big Bang is not an explosion in space. This is one of the most important corrections in modern cosmology. The image people have in their heads of a tiny ball of matter exploding outward into a pre-existing void is wrong. There was no pre-existing void. Space itself did not exist before the Big Bang in the way we usually think about space. The Big Bang was the event in which space started expanding. Every point in our current universe is, in a sense, a descendant of the Big Bang. There is no center. There is no edge. There is no place you can go to find where the Big Bang happened, because the Big Bang happened everywhere. Every cubic meter of space you can see was, at one time, packed into the same hot, dense beginning. That is not what an explosion looks like. That is what the emergence of space-time looks like. And that, again, is uncomfortably close to what a white hole looks like. So the question that some cosmologists have been quietly asking is whether the Big Bang really should be thought of as a beginning at all, or whether it should be thought of as a boundary condition. A boundary, in this sense, is the edge of a region of space-time, not the start of all existence. It is the surface beyond which our equations stop applying, but not necessarily the surface beyond which nothing existed. And one of the most interesting families of theories in modern theoretical physics, which we will get to in more depth shortly, asks whether the Big Bang might have been the emergence of our universe out of some prior structure. A bounce, a transition, a white hole event. Possibly even a white hole event that originated from a black hole in some other universe. Don Page, a Canadian physicist who has worked closely with Stephen Hawking, has written extensively about the cosmological arrow of time and why our universe looks so unusual at its initial boundary. Sean Carroll has spent years arguing that the low entropy of the early universe is one of the deepest unresolved questions in physics, and that any honest theory of cosmology has to address why our universe started in such an absurdly ordered state. Neither of them, to be clear, is saying definitively that the Big Bang was a white hole. What they are saying is that the structural resemblance is real, the entropy puzzle is real, and the solutions to both keep pointing towards something stranger than a simple beginning from nothing. The implication starts to feel almost unbearable when you really sit with it. If white holes cannot exist, then the universe began by violating the same rules that supposedly forbid them, which means either the rules are incomplete, or white holes are not as forbidden as we thought, or the universe really did emerge from somewhere, and that somewhere followed the rules we do not yet understand. None of those options are comfortable. All of them are still on the table, and the more we learn about black holes, paradoxically, the more legitimate the case for the third option becomes. The forbidden object is starting to look less like an embarrassing artifact of the equations, and more like the missing puzzle piece for the deepest question in cosmology. Stay with me. We have a lot more to walk through. Part 8. The conspiracy nobody needs to hide. Before we go deeper, I have to acknowledge something, Because if you have spent any time on the wilder corners of the internet, you have probably already encountered claims about white holes that go very far beyond what I am describing here. White holes attract a particular kind of attention. People online have suggested that white holes are hidden universes, secret portals, the exit ends of wormholes used by alien civilizations. There are claims that NASA has detected white holes and is suppressing the data, claims that white holes are gateways to the afterlife, claims that they are evidence of simulation theory. The fringe interpretations are endless. I want to be very clear here, because I do not want anyone to confuse the legitimate physics with the internet mythology. There is no evidence that any government agency is suppressing data about white holes. There is no confirmed detection of any white hole anywhere in the observable universe, by any telescope, in any wavelength. The conspiracy narratives in this space are not based on real findings being hidden. They are based on misunderstandings of the legitimate theoretical work, amplified through a long game of telephone. That said, and this is the part I think people miss, the actual peer-reviewed physics on this topic is genuinely strange enough that you can see why the conspiracy versions take root. Real working physicists have published, in respectable journals, ideas like the universe being inside a black hole. I am not making that up. The Polish physicist Nikodem Popławski has developed a theory called Einstein-Cartan-Szyama-Kibble torsion cosmology, which proposes that our entire universe lives inside the interior of a black hole that exists in a larger parent universe. In his model, the Big Bang is the moment of bounce that occurred when matter falling into that black hole was compressed and then rebounded, producing what we now experience as the expansion of our universe. The math involves a property of spacetime called torsion, which is something general relativity does not include, but which slightly more general theories do, and the mechanism makes it possible for the singularity at the centre of a black hole to be replaced by a bounce that births a new universe. Popławski's theory is not mainstream consensus. Most cosmologists do not work in torsion cosmology, but it is in peer-reviewed journals, and it is exactly the kind of idea that, when it filters out into popular culture, gets distorted into something that sounds much more conspiratorial than it actually is. The idea that our universe is inside a black hole sounds insane until you realize a working theoretical physicist is publishing on it, and then it sounds insane in a different, more interesting way. This is the thing about the topic. The reason these theories have such persistent gravity in the public imagination is not because of cover-ups or hidden data. It is because mainstream physics itself, even in its most careful, peer-reviewed form, already contains the unresolved possibility that black holes and universes are geometrically connected. The fringe is not making things up out of nothing. The fringe is taking a real, serious thread in theoretical physics and stretching it into something more dramatic. The thread is real. The drama is the embellishment. The forbidden object keeps showing up not because of secrets, but because it is sitting in the equations of the most successful theory of gravity humans have ever produced. People feel that, even when they do not know the math. And that intuition, that there is something here that mainstream science is uncomfortable with, is in some sense correct, even if the conspiracy framing is wrong. Let us get back to the legitimate physics, because the legitimate physics is wilder than the conspiracy theories anyway. Part 9. The information paradox changes everything. In the early 1970s, Stephen Hawking, working at Cambridge, did something that nobody saw coming. He took the basic principles of quantum mechanics and applied them to the empty space just outside a black hole's event horizon. And what he discovered, almost in spite of his own intuitions, was that black holes are not in fact perfectly black. They glow. Faintly, very faintly, but they glow. The mechanism is subtle. Quantum mechanics tells us that empty space is not really empty. The vacuum is a roiling foam of what are called virtual particles, pairs of particles and antiparticles that pop into existence for a moment, then annihilate each other and vanish. Normally this happens too quickly to matter. The pair appears, the pair disappears, and the universe never notices. But near the event horizon of a black hole, something different can happen. A virtual pair can form, and one member can fall across the event horizon while the other escapes. The one that escapes has been, in a sense, promoted from virtual to real. Energy that came from the black hole's mass paid for the promotion. So the black hole, by this process, slowly leaks energy into the surrounding space. We call that leakage Hawking radiation. Over astronomical timescales, this process is extraordinarily slow. A stellar mass black hole, say one with a mass of about 10 suns, would take roughly 10 to the 67th power years to fully evaporate. That is a number so large that the current age of the universe, around 14 billion years, is essentially zero compared to it. By the time stellar mass black holes finish evaporating, the last stars in the cosmos will have died trillions of years earlier. Every galaxy will have come apart. The universe will be unrecognizable. But the math says it happens. Black holes are not eternal. They evaporate. Slowly, painfully slowly, but they do. Now, here is where the trouble started, and here is where black hole physics ran into a wall that we are still trying to climb over. In quantum mechanics, there is a principle called unitarity, which says, in plain English, that information cannot be destroyed. If you know the complete quantum state of a system at one time, you should, in principle, be able to run the equations backwards and recover its complete quantum state at any earlier time. Quantum mechanics is reversible. It does not allow for forgetting, but Hawking's calculation, in its original form, suggested that the radiation a black hole emits is purely thermal, random, containing no information about what fell in. So if you toss a book into a black hole, and then wait an unimaginable amount of time for the black hole to evaporate via Hawking radiation, you are left with nothing but a haze of random structureless particles. The information that made up the book, the patterns of ink, the words, the letters, the meaning, would appear to be simply gone, erased from the universe. Quantum mechanics says that cannot happen. General relativity via Hawking says it does. The two pillars of modern physics when applied together to a black hole, giving compatible answers. We call this the black hole information paradox, and for the past 50 years, it has been one of the most active battlegrounds in theoretical physics. It is the reason a lot of the smartest people alive have spent their careers working on this. Because if we cannot reconcile the two answers, then either quantum mechanics is wrong, or general relativity is wrong, or our concept of black holes is wrong, and nobody wants to give up any of the three. The proposed solutions are wild. Some physicists suggest that information is encoded on the surface of the event horizon and gets released back into the radiation in subtle ways. This is the holographic principle, which led to enormous developments like the AD-CFT correspondence in string theory. Others suggest there is a firewall at the horizon, an actual wall of high energy that destroys infalling matter and preserves the information by force. There is the idea of black hole complementarity, which says that the information is both inside and on the boundary, depending on who is asking, in a way that is logically consistent because no observer can ever see both perspectives at once. But there is another possibility, and this is the one that brings us back to where we started. What if the information is not destroyed, and is not encoded subtly on the horizon, but is simply released later, when the black hole transitions into something else? What if a black hole is not a final destination for matter and information, but a temporary stage in a longer process? What if the information eventually emerges all at once when the black hole turns into its forbidden mirror twin? Suddenly, white holes start looking less like a mathematical embarrassment and more like a solution. Because a white hole is, by definition, a region from which everything emerges. If a black hole transitioned, after long enough, into a white hole, all the information that fell into the black hole would eventually come back out. The paradox would dissolve. The contradiction between general relativity and quantum mechanics would resolve itself, not by either theory winning, but by the structure of black holes being more elaborate than we previously thought. This is why white hole research, after decades on the margins, started coming back into respectable journals over the past 15 years. It did not return because new evidence appeared. It returned because black hole physics itself, the physics of the object we accept and study, broke down badly enough at the centre that physicists were forced to ask what really happens beyond the singularity. And the most natural answer, the one the equations themselves had been quietly suggesting since 1916, was that the other side of a black hole might be its mirror. The modern return of white hole theories comes directly from the failure of black hole theories to be self-consistent. The forbidden object is not a niche obsession, it is a candidate solution to one of the deepest problems in modern physics. Part 10. Singularities may not exist. To understand why this idea of a black hole transitioning into a white hole is taken seriously, you have to understand something about how working physicists react when their equations produce infinities. When a calculation in physics gives you infinity as an answer, that is almost never a triumph. That is a warning. Infinities, in physics, are red flags. They are the equation telling you, I do not apply here. I have hit my own limit. You are asking me a question I am not built to answer. The singularity at the centre of a black hole, the point of supposedly infinite density and infinite space-time curvature predicted by general relativity, is one of those red flags. Penrose proved in the 1960s that under general relativity, singularities are mandatory. If a sufficiently massive object collapses, the math demands that all of its mass be crushed into a single point of zero volume and infinite density. But almost no physicist actually believes that nature literally does this. The consensus instead is that the appearance of a singularity in our equations is telling us that general relativity is incomplete. Somewhere down at the smallest scales, gravity must be merging with quantum mechanics, and the rules must change. The scale at which we expect this to happen is called the Planck scale. It is named after Max Planck, one of the fathers of quantum mechanics. The Planck length is about 1.6 times 10 to the negative 35th meters, which is so small that if you scale the diameter of a proton up to the size of the observable universe, the Planck length scaled by the same factor would still be smaller than a single proton. That is the scale at which we expect spacetime itself to start behaving in fundamentally non-classical ways. And that is the scale at which we have absolutely no working experimental data, because we cannot build a particle accelerator that powerful and probably never will. What we do have is competing theories about what happens at that scale. One of the most developed is loop quantum gravity, which has been worked on for decades by people including Carlo Rovelli, Lee Smolin, Abhay Ashtekar, and Martin Bodgerwald. In loop quantum gravity, space-time is not a smooth continuum. It is granular. It is made of discrete pieces. There is a smallest possible volume of space, a smallest possible area, and you cannot get smaller than that, in the same way that you cannot have less than one electron in a region. The smooth, infinitely divisible spacetime of general relativity is, in this picture, an approximation that breaks down at the Planck scale, in the same way that the apparent smoothness of water breaks down when you zoom in far enough to see individual molecules. There is also string theory, which has its own approach. In string theory, the fundamental objects are not point particles, but tiny vibrating strings, and the geometry of spacetime emerges from how these strings interact. String theory, broadly speaking, also predicts that singularities are not real. The infinity is replaced by something finite, structured and physical, although the details are different from loop quantum gravity. I am not going to wade into the long-running scientific argument between these two camps. What matters for our story is that almost everyone working on quantum gravity, regardless of which approach they prefer, agrees on one thing. Real, infinite singularities are probably an illusion. They are an artifact of using an incomplete theory in a place where it does not apply. If the singularity at the centre of a black hole is not real, if it is replaced by some kind of high-density but finite quantum object, then the entire question of what happens to matter that falls into a black hole gets reopened. Matter falling toward the centre no longer has an infinite point of compression to disappear into. It hits instead some kind of wall, a maximum density, a region where quantum gravity takes over and the smooth predictions of general relativity stop working. And what happens at that wall? That is where the bounce idea enters the conversation seriously. The basic intuition is this. In quantum mechanics, you cannot squeeze a particle into a smaller and smaller box without the particle pushing back harder and harder. This is, very loosely, the uncertainty principle in action. The more confined a quantum object becomes, the more energetic its motion has to be. So if you try to crush an enormous amount of matter down to the Planck scale, at some point quantum pressure resists you. The collapse cannot continue. The infalling matter has to do something other than continue falling. The simplest thing it can do, by symmetry, is bounce. Reverse direction. Start moving outward. Once you have a bounce, the door is open. A bouncing collapse is no longer a one-way street. It is a process with a beginning, a middle, and a continuation. And the continuation, if you think about it carefully, looks an awful lot like the time reverse of the collapse. Matter falling in, then matter pausing, then matter coming back out, black hole collapse, then a moment of maximum density, then a kind of expansion. The mirror image of falling in is of course coming out, which is of course what a white hole does. If singularity is not real, if collapse is replaced by bounce, then the structure of a black hole over its full history is no longer a permanent trap. It is the first half of a longer process. The second half of that process may very well be exactly the forbidden object Schwarzschild's equations have been quietly insisting on for 109 years. The same equations that predicted the black hole, predicted the white hole. If we take quantum gravity seriously, both halves of the prediction may need to come true, just not at the same time. The forbidden object may not be forbidden at all, it may just be on a delay, and that is the idea we're about to crack open. Part 11. The black hole that comes back out. In 2005, an Australian physicist named Sean Hayward published a paper that started, very quietly, to put the bounce model on the map for a wider audience. Hayward proposed that a black hole, instead of containing a true singularity at its centre, contains what he called a regular core, a region of extremely high but finite curvature, where the smooth equations of general relativity are replaced by something more complete. And once you have that regular core, the entire history of the black hole becomes a process rather than a fate. The black hole forms when matter collapses inward. The matter reaches the regular core. Quantum effects halt the collapse. The matter bounces, and eventually the black hole transitions into a white hole, releasing everything it had previously absorbed back into the universe. Now, when I describe this to you, I want to be honest about how strange the timing involved is, because the timing is a huge part of why this entire story is so unsettling. From the inside of the bouncing black hole, the process is fast. Matter falls in, hits the regular core, bounces, and starts coming out. The entire bounce, in the proper time of an infalling observer, might happen in fractions of a second. But from the outside, where you and I are standing, watching the black hole through a telescope, the process takes a very long time. An enormous, almost incomprehensible amount of time, not because the bounce itself is slow, but because of the gravitational time dilation that is at work in the geometry of black holes. When we look at a black hole from outside, we see clocks near its horizon ticking very slowly compared to our own. The closer to the event horizon something gets, the more its time appears to drag from our perspective. So while the infalling matter is, from its own point of view, happily bouncing back through the geometry, from our point of view that bounce is stretched out across a duration that dwarfs the current age of the universe. By the time the white hole stage of the process finishes, from outside it might have been trillions or quadrillions or quintillions of years. The black hole has been sitting in the night sky for what looks, to us, like an eternity. But from the perspective of the matter inside, it was always going to come back out in just a moment. That asymmetry of internal versus external time is what makes the bounce model so peculiar. The outside universe barely notices the process while it is happening, because the timescales involved are so enormous compared to our experience. We see a black hole. We see another black hole. We see them sitting there, doing nothing in particular for billions of years. Meanwhile, in the strange geometry of the interior, a process is unfolding that will eventually, on timescales that might dwarf the universe's current age, complete itself and release everything back out. A bouncing black hole, by this picture, has a regular quantum core instead of a singularity. The information that fell in is preserved through the bounce, because the matter never actually gets destroyed. It is compressed, then released, like a spring. The information paradox in this model simply dissolves. There is no destruction of information, there is only delay. The information is not gone, it is in transit. And the transit is taking a very long time. The emotional implication of all this, if you let it sit, is genuinely shocking. Black holes, in this model, are temporary. The most permanent-looking objects in the universe, the things that astronomers describe as eternal traps, are not eternal at all. They are caterpillars in a chrysalis. They are slow processes whose outputs we have not yet seen, because the timescales are too vast. Every black hole in the night sky, every supermassive monster at the centre of every galaxy, every stellar mass corpse left behind by a dying star, is on a clock. A very long clock, granted, but a clock nonetheless. And when the clock runs out, the forbidden object, the white hole, becomes the natural successor. Hayward's model resolved several paradoxes simultaneously. It eliminated the singularity, which is conceptually awkward. It preserved information, which is required by quantum mechanics. It explained why black holes might naturally end, which solves the question of what happens after Hawking radiation has done its work. And it did all of this without requiring exotic new physics, just a serious application of the principle that quantum gravity probably forbids true singularities. But Hayward's paper was quiet. It did not light up the popular press. It was a careful, technical contribution to a long ongoing conversation. It was not until almost a decade later that a new pair of physicists put forward a much more striking version of the same idea and gave it a name that captured the public imagination in a way Hayward's careful work never quite did. The name was black hole fireworks, and the physicist behind it was Carlo Rovelli. The idea that black holes are temporary is the idea that turns the entire night sky into a delayed explosion waiting to go off. That is where we are headed next. Part 12, Rovelli's Black Hole Fireworks. In 2014, Carlo Rovelli, working with his colleague Hal Haggard, published a paper that put a name on the idea you and I have been circling for the last several minutes. The paper proposed, in technical detail, that black holes do not just sit forever and slowly evaporate. They tunnel. Quantum mechanically, they make a transition into white holes. And when they do, they release their contents back into the universe in what the authors playfully called black hole fireworks. The mechanism behind this is quantum tunneling, which I want to take a minute to explain, because it is one of the most beautiful and counterintuitive features of quantum physics. In classical physics, if you have a ball at the bottom of a valley and you want to get the ball over a mountain to the next valley, you have to push the ball up the mountain. If you do not have enough energy to get it over the top, the ball stays where it is, forever. There is no other option. In quantum mechanics, however, particles do not have to go over the mountain. They can, with some small but non-zero probability, simply appear on the other side. They tunnel. The ball, in a quantum world, could spontaneously be found in the next valley over, even though it never had the energy to climb the mountain in between. This is not science fiction. It is how alpha particles escape from radioactive nuclei. It is how the sun produces its fusion energy, because protons in the sun's core do not have enough thermal energy to fuse classically, and they tunnel instead. Quantum tunneling is real, and it underlies a huge fraction of nuclear physics. What Rovelli and Haggard proposed is that the entire structure of a black hole can quantum tunnel into the structure of a white hole. The transition is not a process that happens piece by piece. It is a single quantum event in which the black hole geometry is replaced by the white hole geometry. The process is wildly improbable on short timescales, but given enough time, the probability accumulates and the transition happens. The black hole spends most of its life behaving like a black hole. Then, at some point, it tunnels, and the same region of spacetime that used to be a one-way trap becomes a one-way fountain. The estimated timescale is, again, enormous. For a stellar mass black hole, the expected time before the transition is roughly 10 to the 64th power years. To compare that to Hawking evaporation, which takes about 10 to the 67th power years for the same black hole, the tunneling transition would actually finish first by a factor of about 1,000, which is to say, in this model, black holes turn into white holes before they finish evaporating. They never get small enough for Hawking radiation to fully consume them. They convert into their mirror twins instead, and in doing so they release everything they had absorbed. The foundations of this model rest on loop quantum gravity. In loop quantum gravity, spacetime is not smooth. It has the smallest possible volume of fundamental graininess. When matter collapses to that smallest possible volume, it cannot be compressed further, because there is nothing further to compress into. The collapse halts, and once the collapse halts, the natural next stage is the mirror process. The geometry, in a sense, undergoes a phase transition, in the same way that water undergoes a phase transition into ice. Spacetime itself changes character, and the change of character is exactly the change that turns a black hole into a white hole. The phrase Rovelli used, black hole fireworks, was meant to describe what the transition looks like from outside. When the transition completes, the material previously hidden inside the black hole is released, possibly all at once. There would be a sudden, enormous burst of energy and matter from a region of space that had previously been an apparently quiet black hole, a firework display, a cosmic flash, a signal that the most permanent-looking object in astronomy had just done something nobody has ever directly observed. This is scientifically controversial. There are critics, there are alternative models. There is plenty of legitimate skepticism about whether the transition actually happens at the rate Rovelli and Haggard estimated, or whether their loop quantum gravity calculation captures all the relevant physics, but it is respected. The paper is in the literature, other physicists have built on it, and importantly, it has spawned a search for observational evidence. If even a few primordial black holes formed in the early universe have already completed the transition, the resulting fireworks should produce signals we could in principle detect: bursts of high-energy radiation, strange transients, anomalies that do not match any other known astrophysical source. There are ongoing efforts to search through gamma-ray data and radio transient data for signatures consistent with black hole fireworks. So far, nothing has been definitively identified. But the search is real, and the theoretical framework that motivates it is published, peer-reviewed, and ongoing in 2026. The implication of all this is what makes me come back to this topic over and over, no matter how many times I read about it. Every black hole in the night sky by this model is going to go off. Every one of them. The supermassive monster at the centre of the Milky Way. The dozens of stellar mass black holes LEGO has detected through gravitational wave bursts. The countless black holes too small or too distant for us to see directly. All of them, eventually, on timescales that dwarf the current age of the universe, are going to tunnel into white holes and release their contents. The universe is not just a graveyard of black holes. It is a nursery of pending fireworks. The universe may not contain eternal prisons, only delayed explosions. And if you're sitting there wondering, has it already happened anywhere? That is exactly the question we have to ask next. Part 13. The first white hole. May already exist. When the universe was very young, in its first fraction of a second, conditions were so extreme and so chaotic that some patches of matter would have been compressed past the threshold needed to form black holes, even without going through the long process of stellar collapse. We call these primordial black holes. They are theorized objects, not directly confirmed yet, but they are taken seriously in cosmology, because the early universe really was the kind of environment in which they could plausibly form. Primordial black holes can, in principle, span an enormous range of masses, from tiny ones smaller than asteroids up to massive ones larger than stars. And the small ones, if they exist, are particularly interesting for our story. Why? Because the timescales we have been discussing for both Hawking evaporation and Rovelli-style tunneling depend strongly on the mass of the black hole. The larger the black hole, the longer it takes to evaporate and the longer it takes to tunnel. The smaller the black hole, the faster both processes happen. A tiny primordial black hole, formed in the first instant of the Big Bang, could have a mass small enough that its tunneling timescale is no longer 10 to the 64th power years. It could be much shorter. It could in fact be short enough that some primordial black holes have already finished their full evolution. They have already collapsed, sat as black holes, tunneled, and emerged as white holes within the lifetime of our universe. If that is true, then somewhere in the cosmos, a white hole has already happened. The transition has occurred. The forbidden object has, at some point in the past, become temporarily real. And if that has happened, there should, in principle, be a signature we could detect. The trouble is, what does the signature look like? Rovelli, working with his colleague Francesco Vidotto and others, has thought carefully about this. The expected signature would be a sudden, brief burst of high-energy radiation, with a particular spectrum determined by the size and properties of the original black hole. It might look something like a gamma-ray burst, those enormous flashes of high-energy light that we already see in the sky from various astrophysical sources. It might look like an unusual radio transient. It might look like a previously unknown class of compact astronomical event. The challenge is that the universe produces many different kinds of bursts and transients, and disentangling a hypothetical black hole fireworks event from, say, a gamma-ray burst caused by a neutron star merger is genuinely hard. There has been some excitement in particular around fast radio bursts. These are millisecond flashes of radio energy that come from distant galaxies, and for a while it was suggested that some of them might be signatures of primordial black hole transitions. The current evidence, however, increasingly points to fast radio bursts being produced by magnetars, which are highly magnetized neutron stars. Most fast radio bursts, as of 2026, are best explained by magnetar activity, so the fast radio burst connection to white holes is weakened. But the broader search continues. The sky is enormous. Telescopes record an immense number of transients each year. The work of figuring out whether any of them is a signature of a black hole turning into a white hole is ongoing. Rovelli and Vidotto have also proposed a concept called Planck stars, which are essentially what is left in the deep interior of a bouncing black hole when collapse halts. These objects in their model are extraordinarily compact and contain the information that fell in. After the bounce completes and the white hole stage releases the bulk of the energy, what is left behind might be Planck-scale remnants, tiny relics of the original black hole that retain certain quantum properties. These remnants would be incredibly small, extremely hard to detect, and could potentially be very long-lived. They could, in some scenarios, even contribute to the dark matter problem, although this is highly speculative. The implication of all of this, again, is what I keep coming back to. If even one black hole anywhere in the observable universe has already completed the full bounce and emerge process, then white holes are not theoretical artifacts. They are physical phenomena. The forbidden object would have moved from the realm of mathematical curiosity into the realm of cosmic history. We would have to take seriously the idea that the universe is doing this routinely, just on timescales we cannot easily observe. The night sky becomes a different kind of place. It becomes a place full of objects that are at various stages of a long process, some of them perhaps very far along, some of them just beginning. The first white hole, if it exists, may already exist. It may have already lit up some patch of the sky in a flash we either missed or recorded but did not yet recognize for what it was. The signature is sitting in some database somewhere, waiting to be identified. Or it may be a signal we have not yet been clever enough to detect. The hunt is on. But while astronomers are out there searching for the fireworks, theoretical cosmologists are asking a different question. What if the relics of these processes are not exotic flashes we cannot find, but a familiar mystery hiding in plain sight? Part 14, The Dark Matter Twist. Dark matter is one of the longest-running unsolved problems in cosmology, and I want to mention it here because it is part of why white hole physics has become unexpectedly relevant to mainstream astrophysics. We know, from the way galaxies rotate and the way light bends around galaxy clusters and the patterns in the cosmic microwave background, that there is something out there providing about 5 times more gravitational pull than all the visible matter we can detect. We have not directly identified what that something is. We have ruled out a lot of candidates. The leading models for decades involved hypothetical particles called weakly interacting massive particles, or WIMPs, but extensive searches at facilities like the Large Hadron Collider have not turned up convincing evidence for them. So physicists in recent years have been broadening their search. They have been reconsidering older candidates that were once dismissed, and one of the candidates that has come back into serious discussion is primordial black holes. Some fraction of the dark matter could potentially be explained by populations of primordial black holes formed in the early universe, particularly after observations from LIGO and from the James Webb Space Telescope have raised new questions about how supermassive black holes formed so early in cosmic history. JWST has, since its launch, found supermassive black holes in galaxies much earlier in the universe than standard models comfortably predict. That observation has sent theorists looking for ways to make black holes early and at unusual masses, which has revived primordial black holes as a serious topic. And here is where white holes sneak back into the discussion. If primordial black holes exist, and if the bounce model is correct, then some fraction of those primordial black holes have already gone through their full evolution. What is left behind after the bounce is finished may be Planck-scale remnants, tiny compact relics that retain mass but are otherwise mostly inert. These remnants would be functionally invisible, since they would not interact with light in any normal way. They would only make their presence felt gravitationally. That sounds, you may have noticed, very much like a description of dark matter. I want to be very careful here, because I do not want to overstate this. There is no confirmed evidence that white hole remnants are dark matter. This is a speculative line of research, not a consensus. The dominant models for dark matter still involve undiscovered particles, and there are many proposed candidates beyond white hole remnants. What I am pointing out is that serious papers in respectable journals have explored the possibility that some fraction of dark matter might consist of relics from completed black hole to white hole transitions. This is not crackpot literature. This is the field genuinely asking what it would mean if the bounce model were correct. If even a small fraction of dark matter turned out to be made of these relics, the implication would be enormous. Dark matter would no longer be an exotic new ingredient added to the universe. It would be the leftover ash of a process that has been quietly going on for billions of years. The hidden half of black hole physics, the white hole half, would not just be relevant to obscure theoretical discussions, it would surround every galaxy. providing the gravitational scaffolding that keeps stars on their orbits and clusters of galaxies bound together. The universe you and I look out at, the one whose gravitational structure depends overwhelmingly on dark matter, would be shaped by the very thing the equations have been quietly predicting for over a century. Black holes, in this picture, are not just oddities. They are increasingly central to cosmology itself. Every time we look more carefully at the early universe, black holes seem to have played a bigger role than we previously thought. Every time we try to solve dark matter, primordial black holes are at least on the table, and the more we engage with the bounce model, the more the second half of black hole physics, the white hole half, starts looking like it might be a structural feature of the cosmos, rather than a forbidden artifact. If white hole remnants contribute to dark matter, then the forbidden object is not somewhere far away. It is everywhere. It is in the gravitational halo of every galaxy. It is part of the structure that lets galaxies form at all. The hidden half of black hole physics may already surround us invisibly. That is a thought to sit with, and it is going to lead us very naturally to one of the more philosophically intense parts of this whole conversation. Because if information survives the bounce, if matter goes in and matter comes out, the obvious question becomes, what exactly is on the inside? What does that interior look like? And what does it mean for the things that fall in? Part 15. What happens to matter? Inside. I want to be careful here, because we are now leaving the relatively well-charted waters of mainstream theoretical physics and entering a stranger region. The questions I am about to raise are speculative. They are extrapolations from the bounce model, not predictions of it. But they are extrapolations that some serious physicists have considered out loud, and I think they are worth thinking through, because they tell us something about what is at stake when we take this line of work seriously. If a black hole transitions into a white hole, and if the matter that fell in is preserved through the bounce, then something has to happen to that matter during the transition. It has to be somewhere. In some bounce models, the matter is simply released back into our universe. The black hole sits in our galaxy, it tunnels, it releases everything it absorbed. The infalling material, in some appropriately scrambled form, comes back into our spacetime. That is the cleanest version of the model, and it is the one most discussed in the published literature. But there is a more elaborate version, which appears in some theoretical proposals, in which the interior of a bouncing black hole becomes causally disconnected from the parent universe. The geometry of spacetime in this picture can do something we're not used to. It can bud off. The interior can become its own independent region, no longer connected to the universe in which the black hole formed. From outside, the black hole eventually disappears. From inside, the bounce produces a new spacetime, expanding outward, unconstrained by the geometry of the parent. A new, independent region. Possibly, depending on the details of the model, a new universe. This is the part where the language starts to fail us, because the words inside and outside lose their normal meaning. In a curved space-time near a quantum gravity regime, the inside of a bouncing black hole is not inside anything in any spatial sense. It has its own time, its own space, its own causality. From its own perspective, it is not a small bubble within someone else's universe. It is everything there is. The parent universe, the black hole that formed it, becomes inaccessible, unreachable. It is not above the new space-time or outside the new space-time in any way that you could point to. It is simply not part of the same causal web anymore. The resulting picture is sometimes called a baby universe. The bouncing black hole, at the moment of transition, gives birth to its own self-contained space-time. From the perspective of that new space-time, the moment of birth looks like a big bang, an outward expansion, an inaccessible origin, an enormous energy release, a low entropy starting condition. You see what I'm about to say, I think. If baby universes can form from bouncing black holes, then the Big Bang of our universe might itself have been the moment of birth of a baby universe inside some parent black hole in some parent universe that we can never access. The reason our universe has the properties of a white hole would be that, from the perspective of our parent universe, it is a white hole. We are, from outside, an emerging white hole event. From inside, we are a Big Bang that produced everything we see. Now, what survives this transition? What carries through? If information is preserved, then in some sense the matter inside our universe is descended from matter that fell into a black hole in a parent universe. The hydrogen in the sun, the carbon in your body, the iron in your blood, would be, on this picture, the deeply scrambled remnants of stuff that once existed in another space-time, fell through an event horizon, was crushed past the Planck scale, bounced, and was reborn as the contents of our cosmos. Identity is a strange word to use here because the scrambling is total. None of the structure of the previous universe survives in any recognizable form, but the conserved quantities, the energy, the information in some quantum mechanical sense, those would have come through. I do not want to overstate any of this. I want to be very honest with you. These ideas are speculative extrapolations. They are not predictions made by a settled theory. There is no observational evidence that our universe was born from a black hole in a parent universe. The mechanism, if it exists, would by its nature leave very few testable traces because the parent universe is, by construction, causally disconnected from us. We cannot send a signal back. We cannot receive one. We can only look at our own universe and ask whether its properties are consistent with this kind of origin. What I find genuinely unsettling, though, is that the properties of our universe are not just consistent with this kind of origin. They are exactly what this kind of origin would predict. Outward expanding space-time, inaccessible past, enormous initial energy, profoundly low initial entropy. These are not features that the universe was somehow forced into despite a different actual origin. They are the natural consequences of being the inside of a white hole birth event. The tone here is meant to be careful, not certain. We are looking at a possibility. We are not looking at a conclusion. But the possibility is real enough and substantial enough that working physicists have built theories around it. And once those theories exist, the next question almost asks itself. If universes can give birth to other universes through black holes, then are we perhaps just one generation of something larger? Is there a family tree? The ideas we're about to explore are, in my opinion, some of the most genuinely original ever proposed by serious scientists, so let us step into them carefully. Part 16. Lee Smolin's Dangerous Idea. In 1992, the American theoretical physicist Lee Smolin published a paper that contained one of the most underappreciated ideas in 20th century cosmology. He expanded on it more fully in his 1997 book, The Life of the Cosmos, where he gave it a name that captures its essence with almost unnerving clarity. Cosmological natural selection. Smolin's idea is the kind of thing that, when you first hear it, sounds either ridiculous or brilliant, depending on how you interpret it. It might be both. The proposal is this. Universes, like organisms, can reproduce. The reproductive mechanism is the formation of black holes. Each black hole that forms in a universe, on this picture, eventually buds off a new region of space-time, which becomes a baby universe with slightly different physical constants from its parent. Universes that produce more black holes leave more descendants. Universes that produce fewer black holes leave fewer descendants. Over many generations of cosmic reproduction, the population of universes becomes dominated by the kinds of universes that are good at making black holes. We, sitting in this universe, are likely to find ourselves in one of those black hole fertile universes, not because anything chose for us to be here, but because statistically that is where most observers like us would be. I want to walk you through why this is genuinely powerful as an idea, regardless of whether it turns out to be correct. The biggest unsolved problem in fundamental physics, arguably, is the fine-tuning problem. The constants of nature, the strength of gravity, the masses of the fundamental particles, the strength of the strong nuclear force, the cosmological constant, all of these have very specific values. And if any of them were even slightly different, our universe would look completely unlike the one we observe. Stars would not form, atoms would not be stable, chemistry would not work, life in any form recognizable to us would be impossible. The constants of physics seem to have been set with extraordinary precision to allow the existence of complex structures. The standard ways to explain this are unsatisfying. One explanation is that the constants were chosen by some intelligent designer, which is not a scientific theory because it is not testable. Another explanation is the anthropic multiverse, which says there is a vast number of universes with different constants, and we happen to live in one with constants that allow life, because we cannot live in one that does not. The anthropic argument is logically valid, but it has been criticized for being scientifically empty. It does not predict anything. It just notes that we would not be here to observe a hostile universe. What Smolin did was propose a third option, The constants are not chosen by a designer, and they are not just a random sample from a vast multiverse. They are the result of a Darwinian process. Universes that are good at making black holes, by virtue of their constants, leave more offspring. Over many generations, the constants drift toward values that maximize black hole production, and possibly, those same values happen to be ones that also support complex chemistry, stars, and life, because some of the same conditions that allow stars to live and die and collapse into black holes also allow planets and biology. The theory makes a testable prediction, which is rare for ideas this speculative. Smolin argued that if cosmological natural selection is correct, then our universe should be very close to optimal for black hole production. Any small change in any of the fundamental constants should make black hole formation harder, not easier. If instead you discovered that you could change one of the constants and produce more black holes, that would falsify the theory. So far, no obvious falsification has emerged, although the theory has been criticized and the predictions are subtle. The reason Smolin's idea matters for our story is that it requires white holes structurally. The mechanism by which a baby universe forms inside a black hole is essentially the bounce we have been discussing. The black hole collapses, bounces, and produces an outward expansion which, from inside, looks like a new Big Bang. That outward expansion is a white hole event, in the relevant sense. So Smolin's theory makes white holes not exotic anomalies, but the reproductive organs of the cosmos. They are how universes have offspring. Universes on this picture have ancestry. Our universe has parents. Our universe has grandparents. There is somewhere out there, in a sense that bends the meaning of out there past its breaking point. A lineage. A family tree of cosmoses, branching across generations, with each generation slightly different from the last, drifting in the direction of conditions that favour black hole production. We are sitting in a leaf at the end of one of those branches, looking up at a sky full of black holes, and our existence is connected to the black holes in our sky in a way that, if Smolin is right, is far more intimate than we ever imagined. The forbidden object is not just permitted in this picture, it is essential. The forbidden object is the link between generations. It is the channel through which universes give rise to other universes. White holes may not be forbidden anomalies at all, but the reproductive mechanism through which universes generate new universes. Part 17. The Universe Family Tree. Let us imagine this picture for a moment, just to feel its full weight. Imagine our universe as one node in a vast family tree of cosmoses. Above us, in some abstract sense, is our parent universe, the cosmos in which a black hole formed and bounced and gave birth to ours. Above that, our grandparent universe, and our great-grandparent, and so on backwards, however many generations the lineage has had. Each ancestor universe had its own physical constants. Each was a slight variation on its predecessor. Each, if Smolin's mechanism is correct, was a little bit better at making black holes than the one before, because the universes worse at making black holes left fewer descendants and got pruned from the tree. Below us, in the same abstract sense, are our descendants. Every black hole that has formed in our universe is, on this picture, a potential offspring. Stellar mass black holes from collapsed stars, supermassive black holes at the centers of galaxies, primordial black holes from the early universe. Each one, when it eventually transitions, will give rise to a new universe with its own slightly different physical laws. Some of those descendant universes will be more fertile than ours, some will be less. Over enough generations, the population converges toward whatever set of constants maximizes black hole production. Smolin, working with the philosopher and political theorist Roberto Mangabeira Ungar in their 2015 book The Singular Universe and the Reality of Time, expanded on these ideas to suggest that even the laws of physics themselves might evolve across generations. The constants, in this fuller picture, are not the only thing that mutates. The laws, the equations, the very structures of physical reality might drift and change in the same way that biological forms and developmental rules evolve in living organisms. Universes might inherit their physics from their parents, with mutations, and the lineage that succeeds is the lineage with rules that produce more lineage. This reframes fine-tuning in a way that is genuinely strange and, I think, beautiful. The reason our universe has constants that are perfect for stars and chemistry and life is, on this view, almost incidental. The constants are perfect because they are also good for black holes, and the universe is selecting for black hole fertility, not for life. Life is a side effect. Life is a byproduct of conditions that favour stellar evolution and gravitational collapse. We are not the goal. We are something the universe happened to grow on the way to making more universes. I find that thought genuinely vertiginous, and I'm going to sit with it for just a second. Humanity is, in this picture, not the purpose of cosmic history. We are not the reason the universe exists. We are an emergent property of a process whose actual function is reproduction. Our universe is a black hole factory, and we are the moss growing on the side of the factory while it works. That is a humbling recentering. It is also, in a strange way, freeing. We are not under any obligation to be the meaning of the universe. We get to just be us, growing on the side of an enormous reproductive engine that does not need us to justify itself. The Big Bang itself on this picture is not the start of all reality. It is just the moment our particular branch of the family tree split off from a parent. The forbidden object, the white hole, is the umbilical cord. The entire cosmos in which we live, with all its galaxies, all its stars, all its rocky planets and oceans and life and minds, is on the inside of a white hole birth event that occurred in some parent universe we will never see. Our entire history is the inside of one frame of one branch of one cosmic family tree. The Big Bang itself, then, may have been the white hole birth event of our own universe's lineage. The forbidden object may not be forbidden. It may be the most important kind of object there is. It may be how cosmoses come to be at all. Part 18, the black hole at the centre of the Milky Way. I want to bring this back down to something concrete, because all of these ideas can start to feel abstract and detached, and I think it helps to anchor them to a real object. Right now, 26,000 light-years away from where you are sitting, there is a black hole called Sagittarius A. It is the supermassive black hole at the centre of our own galaxy, the Milky Way. We have not photographed it directly with the kind of clarity we got for the M87 black hole, but the Event Horizon Telescope did produce an image of it in 2022, and we know its properties extremely well. It has a mass of approximately 4 million times the mass of our Sun. It is sitting there, right now, doing what it has always done, which is anchoring the gravitational structure of the entire Milky Way. Sagittarius A star is real. We can detect it. We can track stars orbiting it, and watch their orbits bend in exactly the way Schwarzschild's 110-year-old equation predicts. It is not a thought experiment. It is not a piece of speculative fiction. It is a 4 million solar mass piece of cosmic furniture that has been part of our galaxy for billions of years. Now, take everything we have been talking about and apply it to that one object. Sagittarius A star, in the bounce model, is on a very long clock. Right now it is collecting matter. Stars that wander too close get torn apart by tidal forces and partially absorbed. Gas clouds drifting through the galactic centre get drawn in. Dust, cosmic rays, the occasional unfortunate planet swept inward by encounters with other stars, all of it slowly accumulates. Sagittarius. A star has been growing for the entire history of our galaxy, and it will keep growing for billions of years to come as the Milky Way itself evolves and eventually merges with our neighbour Andromeda in roughly 4 billion years. But the bounce model says, somewhere down a road that is so long it makes the current age of the universe look like a single tick of a clock, Sagittarius. A star will not just sit there. It will not just slowly evaporate. It will eventually undergo the transition. The geometry that has been a one-way trap for billions of years will reverse character. The black hole will become a white hole, and everything it absorbed during its long life will be released, possibly all at once, possibly in a transition that, from the perspective of any future observer, looks like a sudden rebirth of energy in a region that had been quiet for unimaginable lengths of time. If Smolin is right, that transition is also the moment of birth of a new universe, a baby cosmos, with slightly different constants, expanding outward from inside what was, at the moment of transition, the black hole at the centre of our galaxy. That baby universe will be causally disconnected from us. It will not affect our spacetime. It will have its own time, its own geometry, its own history. From the inside of that universe, the moment of transition will look like a Big Bang. There will be expansion outward. There will be an inaccessible origin. There will be an enormous energy release. And there will be a low entropy initial condition, and somewhere in that baby universe, billions of subjective years later, on some planet that we will never see, and could never reach. An intelligent species may someday emerge, look up at their own night sky, and ask the same questions you and I are asking right now. They will not know that their universe began inside what was, at the moment of birth, a black hole at the centre of a galaxy in a parent cosmos. They will only see their own beginning as a strange low entropy boundary in their own past, and they will wonder what it means. The black holes we observe today may become the future Big Bangs of entirely new universes. Sagittarius A star may, given enough time, become the origin point of someone else's cosmos. And the people in that cosmos, if there are any, may someday sit and watch this kind of video and think the same things we're thinking now, in a feedback loop that stretches across cosmic generations. I find that thought, more than almost any other I have ever encountered, both terrifying and consoling at the same time. Terrifying because it makes us so small, consoling because it makes us part of something so much larger. Part 19. What would prove any of this? Let me bring us back just for a few minutes to the ground, because I have been describing ideas that, if they turned out to be correct, would change everything we think about our place in the cosmos, and I owe you an honest accounting of how confident we should be in any of them. The honest answer is, not very. None of what I have just described has been observationally confirmed. There is no confirmed white hole anywhere in our records. There is no confirmed bouncing black hole. There is no confirmed evidence of cosmological natural selection. Quantum gravity, the framework that underlies the entire bounce mechanism, has not been experimentally verified. The Planck scale is so far below what any current technology can probe that we are essentially guessing about the rules that apply there. Our best ideas are, at this point, theoretical proposals motivated by indirect arguments about consistency, beauty, and the resolution of paradoxes in known physics. There are possible future tests. Some of them are not impossible. Gravitational wave detectors, especially as they become more sensitive over the coming decades, might pick up signatures from black hole transitions that current detectors cannot resolve. If the bounce model is correct, the merger of two bouncing black holes might produce a slightly different waveform than the merger of two classical black holes. The differences would be small, but they might be detectable. Future generations of detectors, possibly including space-based instruments like LISA, may be sensitive enough to look for them. Hawking radiation, although it is too faint to detect from any real astrophysical black hole, might be measured indirectly through cumulative effects, and any deviations from the predicted spectrum might tell us something about whether bounces are happening. Searches for the firework signature, the sudden burst from a primordial black hole completing its transition, are ongoing, and large-scale sky surveys are now collecting data at a rate that makes systematic searches for unusual transients possible. Searches for primordial black hole remnants as candidates for dark matter are ongoing, and refinements in our ability to map the dark matter distribution might rule them in or out as a significant component. But all of these tests are indirect. They are hard. They require enormous patience, enormous instrumentation, and the kind of theoretical work that takes decades to either confirm or rule out a given proposal. The mainstream physics community, broadly speaking, treats these ideas with a mixture of interest, skepticism, and patience. Most working physicists are not convinced in the way they are convinced of, say, general relativity or quantum electrodynamics. They view the bounce models, cosmological natural selection, and the white hole interpretation of the Big Bang as live possibilities worth investigating, not as established truths. Falsifiability matters, and I think it is important to acknowledge that some of the ideas in this conversation do not have clean falsification criteria yet. That is one of the reasons they have not been promoted to mainstream consensus. Without sharp predictions that can be tested against observations, ideas, no matter how elegant, remain in a kind of theoretical limbo. They might be right, they might be wrong. The work of moving them out of limbo in either direction is exactly what physicists are slowly doing. The mystery remains unresolved because modern physics still cannot experimentally determine whether black holes truly end or whether they transform. The forbidden object cannot be ruled in or ruled out by current technology. We are stuck, for now, in the interesting position of having a coherent and beautiful set of theoretical ideas that we cannot yet test. That is normal in physics. That is how every revolutionary idea begins. Black holes themselves were treated this way for 50 years before they were observationally confirmed. White holes are at the stage, black holes were in the 1960s. They are taken seriously. They are not yet established. The question of which way the evidence will eventually fall remains genuinely open, so I cannot tell you that any of this is true. I can only tell you that it is on the table, in legitimate journals, and that the people working on it are not fringe figures. They are some of the best theoretical physicists alive. The question of what is on the other side of a black hole is, in 2026, not a settled question. It is a frontier. Part 20. The final inversion. I want to bring us back to where we started, you and I, and walk you slowly through the inversion that I think this whole conversation forces. We started, all those words ago, with the framing of the forbidden object. Schwarzschild's 1916 equation predicted two structures. We accepted one and quietly ignored the other for 109 years. Black holes became real. White holes became an embarrassing footnote. That was the picture we began with. Then we walked through the trench, where Karl Schwarzschild, dying of a disease he did not know was killing him, wrote down by candlelight the most consequential equation in 20th century cosmology. He did it in weeks. He did it under artillery fire. He never knew what he had done. He died in May of 1916, having unknowingly given humanity the equations that would later let us photograph a black hole, detect gravitational waves, and ask questions about the very structure of spacetime. The equation he wrote contained both objects. He did not get to choose which one we accepted. Then we walked through entropy and the second law of thermodynamics, and Penrose's almost unbelievable estimate of the specialness of the initial state of the universe. 1 part in 10 to the 10 to the 123rd power. We learned that the Big Bang requires a low entropy starting condition that, by every measure we can apply, looks impossible. We learned that white holes also require low entropy initial conditions, which is the very property that makes them seem forbidden. Then we walked through the bounce. We learned that the singularity at the centre of a black hole is probably not a real, infinitely dense point of matter, but a warning sign that general relativity has hit its own limits. We learned that quantum gravity, in its various forms, suggests that collapse cannot continue past the Planck scale. We learned that, if collapse halts, the natural continuation is reversal, and we learned that Carlo Rovelli and Hal Haggard, in 2014, proposed in detail that black holes quantum tunnel into white holes on enormous but finite timescales, releasing everything they had absorbed in a process they called black hole fireworks. Then we walked through Smolin's lineage theory, and the idea that universes might reproduce through black holes, with each black hole eventually budding off a new universe with slightly different physical constants. We saw that, in this picture, the constants of our universe are not fine-tuned for life by design or by sheer accident, but by a Darwinian process that selects for black hole fertility. We saw that life is a side effect of black hole production, not the goal. And then we sat with Sagittarius A star, the 4 million solar mass black hole at the centre of our own galaxy, and asked what its long-term future looks like. We saw that, in the bounce model, that black hole is on a very long clock. We saw that, eventually, if the model is correct, it will release everything it has absorbed in a sudden burst and may give birth to an entirely new universe in the process. So now let me ask you the question I have been holding back. Where does that leave us sitting here, looking up at our own night sky? It leaves us, I think, in a profoundly inverted position. We started by treating white holes as exotic exceptions, as mathematical curiosities, as objects the universe forbade. Now, look around. The universe we live in began with the entropy of a white hole. It expanded outward like a white hole. It has an inaccessible origin like a white hole. It carries the structural signature of the forbidden object in every property we can measure. The Big Bang, the founding event of all of cosmology, looks like a white hole birth event from inside. Maybe white holes are not rare. Maybe the universe itself is evidence of one. Maybe we have been so focused on the absence of white holes elsewhere that we missed the fact that we are standing inside one. Maybe the reason the night sky does not show us obvious white hole flashes is not that white holes are forbidden, but that we are inside the one we should be paying attention to, and the rest are still in progress on timescales we cannot yet observe. Maybe the question is not whether white holes exist, but how many generations of them came before us. I want to be careful, again, to emphasize that none of this is confirmed. I am not telling you that our universe definitely came from a black hole in a parent universe. I am not telling you that Sagittarius A star will definitely, someday, become the Big Bang of a baby cosmos. I am not telling you that cosmological natural selection is correct. What I am telling you is that every major piece of this story emerged from legitimate attempts to solve real problems in physics. The information paradox is real. The entropy puzzle is real. The singularity problem is real. The fine-tuning problem is real. The fact that the Big Bang structurally resembles a white hole is real, and it is something working cosmologists have been quietly noting for decades. Each of these problems, taken alone, has multiple proposed solutions. But it is striking that the solutions that work for all of them at once tend to involve, at some level, the structures Schwarzschild predicted in his trench: black holes that bounce, white holes that emerge, universes that reproduce, the forbidden object, reframed not as a violation, but as a foundation. I want to leave you with one image, before we let this end. Picture the night sky. Look up. You can see, even from a city, a few stars. From a dark site you can see thousands. Most of those points of light are stars, but a small fraction of what is up there, by the count of every modern survey, are objects you cannot see directly. There are, conservatively, hundreds of millions of stellar mass black holes scattered through the Milky Way alone. Across the visible universe, the count rises into numbers that I find genuinely overwhelming. Trillions of black holes. More than there are humans who have ever lived. More than there are grains of sand on every beach on Earth. All of them sitting there, in the dark, doing what black holes do. In the deep future, in a future that makes the current age of the universe look like a single heartbeat, every one of those black holes is going to face the same long process. Some of them will fully evaporate via Hawking radiation, if that is what happens. Others, if the bounce model is correct, will tunnel into white holes and release their contents back into the universe, possibly giving birth to baby cosmoses in the process. The night sky, the one you have always thought of as a still photograph of points of light, is actually a slow-motion fireworks show, paused so close to a single frame that you cannot see the motion. But the motion is there. It just unfolds on timescales that dwarf our perception, and somewhere out there, tonight, while you're sitting wherever you're sitting, watching this video on whatever screen is in front of you, one of the oldest black holes in existence may already be beginning to turn itself inside out. The transition may have just started, or it may have started 1 billion years ago, and the signal of that transition may already be on its way to us, travelling across the gulf of intergalactic space at the speed of light, due to arrive someday, somewhere, in the data of some future telescope. The night sky may be hiding the most important event we have ever been on the verge of detecting. Karl Schwarzschild died in 1916 in a hospital of a disease that kept him from ever knowing what he had given us. He never heard the phrase black hole. He never heard the phrase white hole. He never knew that his equation, written in a trench during the worst war the world had ever seen, would become the foundation of how humans would think about the structure of reality itself a century later. He never knew that the second object in his equation, the one we have spent 109 years trying to wave away, might turn out to be the reason we exist at all. The equations predicted 2 impossible objects. We confirmed one. The other may be the reason the universe exists at all. Sleep on that, friend. I will see you in the next one.